so that there's also VOD for YouTube later. Will we look at time complexity today? Yes, we will look at the time complexity of some of the graph problems and data structures, or implementations. Yes, yes. All right. If there's more questions, feel free to type them up while I introduce the first topic. So last time we talked about what a graph looks like, right? Vertices, edges, paths, cycles, adjacency, all these kinds of properties that vertices and edges can have as they together make up a graph. Today I want to see, okay, but how do we actually build one of these graphs into a computer? Well, there's a variety of options we can choose from. So one option is what we call an edge list. We say, well, a graph is nothing more than just a set of edges. Obviously, we've seen last time that this isn't true, right? We can also have, or a graph is actually a set of vertices and a set of edges. But in some implementations, we say, well, there's just a list of edges. And with that, we can do quite a lot. The only thing that might go wrong is when we have a vertex without any edges, because there's no way to represent that in one of these edge list implementations. But other than that, we can make most operations work. Alternatively, we could have an adjacency list implementation. What do? Well, we say our graph is just a bunch of edges, a bunch of vertices, and every vertex has the list of edges, all of its incident edges. So if it's directed, we could maybe split them out into ingoing and outgoing. But if it's undirected, then just a list of edges. And again, this is an implementation that allows us to do pretty much everything we want. There is adjacency matrix, where we just have a massive 2D array. And we indicate in this array whether an edge exists or not. So the array is of size v by v, and we can just indicate which edges do and do not exist by putting true or false, or indicators of a weighted graph and number in the right place in the array. Consider, for example, that an edge exists between vertex 5 and vertex 3. Then we could have a true or a certain weight in row 5, column 3. Now these are all great, and they're used quite a bit because they are the, let's say, easiest implementations to make for a graph. But the one I prefer most is adjacency map, which, well, when you take a look at the time complexities of the operations, adjacency map is always equal or better. So that's the one I think is most worthy of our attention. So what's the idea with an adjacency map? Well, for that, let's switch over to WebLab, because I have an assignment for WebLab prepared for you. Let me see if I can get it up here. Firefox, there we go. Let's make this a bit bigger. So what's the idea with an adjacency map? Well, in an adjacency map, and you'll be implementing this in a moment, we have not a list of vertices, but a map of vertices. The key is the index of the vertex and the value is the vertex. So that's part one. So a graph has a dictionary of vertices, and every vertex has a dictionary of its adjacent vertices. So what does that mean? It means that, let's say we take vertex 3 again. If it's connected to vertex 5, then the adjacency map of vertex 3 contains an entry 5 as the key, and as its value, the vertex number 5. And this allows us later to very quickly see, okay, are 3 and 5 connected? Because what do? Well, we simply check whether in vertexes 3 adjacency map, is the key 5 there. And as you remember, hopefully, from our discussion on Monday, this contains check on a dictionary or in a map is expected O1, expected constant time. So compared to the other implementations, well, compared especially to adjacency list and edge list, we can check in constant time whether two vertices are connected. Now, we could also do that in an adjacency matrix, but an adjacency matrix wastes a lot of space, right? It's always going to be of size v times v, whereas this map is only going to be as big as it needs to be. Okay, I think that's enough talking from my end. I suggest you take a look at this exercise. There's a couple of functions that we need to implement. I'm going to give you about 15 minutes. Now, normally, of course, I'd walk around and answer some questions. That's going to be a bit harder, but I'll keep an eye on chat so you can post some questions there if you have them. And like always, please do also indicate there when you're done, because if it turns out that out of the 25 people watching, 20 are done after 10 minutes, then we can cut it a little bit early. But I'm going to give you about 15 minutes. Try and see if you can implement these different functions while I get my webcam working. See you in a bit. Okay. Now, based on the statistics that WebLab is able to show me, combined with the fact that no one has yet indicated that they're done in chat, here's, I suppose, what we, or here's what I propose we do. I'll show you how to implement the first two methods, init and add vertex. And then I'm gonna give you, maybe also contains edge. Yeah, that sounds like a good idea. And then you can take another few minutes to see if based on that you can figure out add edge and remove edge. So let's take a look. Initialize. What does our assignment say? This is the constructor of the graph. You will have to initialize the attributes that this graph has. Okay, so this graph has two attributes. It has a size. Well, when we create a new graph, there's nothing there yet. So we should set the size to 0. And it should have something to store the vertices. That should be a dictionary. All right. Remember that, of course, you can also initialize dictionaries like this, right? Either works. Then, adding a vertex. This function adds a vertex to the graph. The index number of the new vertex will be one more than the highest index of all existing vertices. Okay. Sounds perhaps somewhat complicated. But what does that mean? Well, it means that what we can do is we can use the size to determine the index of the vertex. Because when we have no vertices, well, then how about we make sure that the first vertex we add is ID 0. Now let me just see how we initialize a vertex. A vertex only needs an index to be initialized. So new vertex self.size, self.vertices. So now we need to store it in here. Well, this was a dictionary with an integer and the vertex. So its ID, I might as well do this like this. New vertex.index will store the new vertex. And finally, we need to increase our size by 1. So what happens? Well, the first vertex we add will have an ID of 0. And next time I add one, it will have an ID of 1. And the next one will have an ID of 2, and then an ID of 3, and so on and so forth. Gideon is raising a valid point, right? Won't this mess it up when we remove vertices? Yeah, but I've peeked ahead a bit, and remove vertex is not something we need to implement today. That's the cheeky answer. If you prefer, what you could of course also do is something like this. I think this is how it works in Python, but I'd have to Google that. Python get all keys from a dictionary. I thought it was just dot keys. Yes. Yes. Right, then you find the maximum value and you add 1. So if you allow removal of vertices, this could be a solution. Does that make sense, Gideon? All right. Okay. Okay. So what have we done? We've made an initializer, right? Start the size at 0 and start with no vertices. We've implemented add vertex. Now I also want to implement contains edge, and then I'm going to give you a little bit more time to look at add edge and remove edge. So contains edge, what would we do? We want to know, is there an edge between v1 and v2? Okay, Well, if V1 is in self.vertices, right? So if V1 exists at all, then you should check whether V2 is in the neighbors of V1. And otherwise you should return false. Siroy, you're asking, does this also do the same thing? And you give some nice expression where you basically combine these two statements. Oh, hang on. My Python syntax here is broken. It should read this. Right, self.vertices in the place of the index should equal the new vertex. And so Siroy, yes, you can also combine them in the way you are suggesting, where I immediately put this over here and replace this with self.size. That would also work. Jochem, you're asking, but shouldn't we check whether it also exists the other way? Fair. Now keep in mind, we will be implementing add edge. So what we can do is we can make sure that every time we add an edge between V1 and V2, we add it both ways. And then for our contains, you could add this check, but it should never be the cause of failure, right? If one is in the other, or if V1 is connected to V2, then V2 should also be connected to V1. We can make sure of that with add edge, if that makes sense. All right, then I'm gonna give you another couple of minutes, let's say about 4, to take a look at add edge and remove edge, and then we'll take a look together. See you in a bit. Again, if you have any questions about what we've done so far, feel free to ask me via chat. If you are done, please let me know via chat, and I'll see you in a bit. Okay, so let's see if we can figure it out. So we need to add a new edge to the graph. V1 and V2 are the indices. Okay, let's see what it says over here. This function adds an edge to the graph. Note that a vertex can't share an edge with itself. Aha. Okay, so maybe start with that bit. It can't share an edge with itself. So what does that mean? Well, it means that when V1 equals V2, we should do nothing. Otherwise, we actually need to do something. And what do we need to do? Well, in self.vertices, let's find vertex V1. And to its adjacency map, we should add V2. So you might think, okay, maybe we need to do something like this. Unfortunately, that doesn't quite work. Remember that adjacency, or adj, is also a dictionary. So in order to put something in there, I need to give the key and I need to give the value. There we go. I want to make an edge from vertex 1 to vertex 2. And of course, I also want to do that the other way around. From vertex 2, I want to add an edge to vertex 1. Now, if you want, it might be nice to also include in here a check to see whether V2 or V1 and V2 are actually vertices that exist. Because otherwise lines 45 and 46 throw an error. Now our tests are nice this time around and they don't have vertices that don't exist, but but this is perhaps the slightly cleaner way of doing it. Jochem, you're asking, could we also do this? Well, there's a small problem here, because this thing will create a new node with the same index as an already existing node. So we could not have, so if we do, for example, self.vertices.v1 dot adjacency v2, right, to get vertex 2, we would find a different vertex 2 than when I say self.vertices v2, right? So if we do it like this, then the neighbor of v1, this one, would not be the same object as this one. So yeah, if you want to think of it like that, it sort of makes a copy, you're right, only a copy that does not have all of the neighbors that we may have already added to self.vertices v2, right? So it really makes a new node without any edges and assigns that as the value in this dictionary, if that makes sense. Good, okay. So good idea, but we should really make sure to reuse the vertex. Then Xijing, you're asking, shouldn't you use and instead of or in the if statement? I don't think so, right? These are three conditions that would make sure I don't want to do it if one of them is true, right? If it would be a self loop, I don't want it. If v1 does not exist, I do not want it. And if v2 does not exist, I do not want it. Sorry, or if v2 does not exist, I do not want it, right? One of these is enough to cancel everything. Okay, then let's take a look at remove edge. So what should I do here? Well, I need to, let's read the text first. This function removes an edge from the graph. Okay, nothing new there. I need to tell Python to delete a key from a dictionary. And this is how we do that. So I want to remove the edge between V1 and V2 and also between V2 and V1. Again, it wouldn't hurt to have this check first, right? Check whether V1 and V2 exist before trying to delete them. But again, our tests are not nasty, so without this it should also work. Okay, let's see if this was enough to make it all work. So we pass all the your tests and we pass all the spec tests. So this should be it. Are there any questions about this? While I set up my slides to tell you two small things before we go into our break. I see no questions at the moment. I'll put my code back up during the break and then you can take another look. Is that okay, Yara? I will talk a little bit more first and then during the break I'll make sure my code is available to you. So, we took a look now at an adjacency map. In my slides, which I will publish later, you will find a slightly different implementation of an adjacency map. It does the same thing, but it's slightly different. So I'm not going to go through that now. We just implemented one ourselves. Now, the implementation that we created is better than all the others that are in the book. And tomorrow is, well, just now. Because what time complexities do we have? Well, to get the vertices is just theta 1, right? It's just graph.vertices. To get the edges, okay, that actually requires us to go over all the different vertices. But we could also keep a track of a separate list of edges and then, or perhaps just a counter. And then we could make this constant time as well. Determining the degree of a vertex, well, that's just getting the size of one of these adj fields, or the len of one of these adj fields, so that's constant time. Getting all the neighbors, well, it takes no more time than there are neighbors, so theta degree of v. Adding a vertex, adding an edge, both constant time, because all we're doing is adding something to a dictionary, and adding something to a dictionary is expected constant time. And there's a whole bunch more operations. So for example, we implemented contains edge, right? Also in constant time, because again, a contains check in a dictionary is expected constant time. But there's more operations. Now, the question is, what operations should you implement? For example, we implemented remove edge, but we did not implement remove vertex. Well, the answer is, yeah, stupid as that may be, it depends, right? It depends on what you want to use your graph for. What kind of functionality do you need? And you should make sure your graph provides that. So you will also find that when I give you graph implementations later on to perform certain algorithms, for example, after the break, we will be implementing breadth first search. That implementation might be slightly different from the implementation you've seen just now, but that is because we want to do slightly different things with it. So we will make sure that when we give you a graph, it has all the functionality you need, and maybe a little bit more, but definitely everything you need. Okay. Then, after the break, we will be talking about graph traversals. Let me answer one more question first. So why is the degree theta 1? Well, if you look at our code, Jochem, then here we go. What you see is that to get the degree, what would we have to do? I can even just write it here. We would simply return. So let's say I wanted to get the degree of a certain vertex v1, right? I would just return self.vertices.v1, self.vertices v1's adjacency maps length. So I need to get something from a dictionary, that's constant time, and I need to determine the size of adje, but Python is smart and it keeps track of the sizes of dictionaries, so this is also constant time to determine that size. So getting the degree is just this line, and that's just constant time. Okay, with that, I'm gonna send you off into a break. I will make sure my code is visible on stream in the meantime, and I'll stick around in chat if you have any questions. See you in a bit. All right, so let's try to get started again. Just after the break means that normally it would be time for today's intermezzo, but some bad news on that. I planned for this to be a very interactive intermezzo in which we would take the tables from Pulse Hall 8 and construct ourselves a little maze similar to the thing that you're currently seeing in this YouTube video that I have on screen. Because earlier this year, a couple of months ago, I made a video in which I execute a graph traversal algorithm in a graph visually represented as a maze here. And I do what we call a depth-first search to find the solution to the maze. It's a video that's currently still unlisted because I wanted to polish it a little bit more, but I think I'll just publish it later today. I walk around this thing for a bit and I finally manage to find my way out of the maze. There we go. I was planning to do something similar in class with you building a maze and then me or one of you executing depth-first search on this. Unfortunately, that's not going to work. However, after I've talked about depth-first search for a little bit in a moment, if you feel inspired and you're looking for something to do while sitting in your house all day, why not build your own maze in your living room and see if you can use depth-first search to get out of that one. So, short intermezzo, no interactive intermezzo as I had planned, but let's crack on regardless. And let's talk a little bit about graph traversals. Let me hide this. There we go. So we've seen different ways of traversing trees. Now let's take a look at different ways of traversing graphs. And this is going to be the first of these 4 questions that I formulated together with you last Tuesday. The first of these 4 questions that the NS might be asking, right? Or that we might be asking about the NS. And the first question was, given the state of the current network, can I get to Haarlem? Remember, when I was a student, I lived in Haarlem, so this was a question I would ask every day, can I get home today? Well, to answer that, we can use a breadth-first or a depth-first search. What does that mean? Well, for a depth-first search, imagine you are walking in a labyrinth. And you might be familiar with the Greek myth of Theseus, I think he was called, who went into the labyrinth of Crete to defeat the Minotaur. And he was armed with nothing more than a piece of rope. Now, and maybe a sword to actually kill the Minotaur with. But in terms of navigation through the maze, all he had was his rope. Now, I've never found that myth quite credible, because I feel that in addition to the rope, you also need paint. But with those two together, we could make it work. So how would that work? Well, you bring your paint and you bring your rope, and first thing you do is you tie the rope to the entrance. Now you start walking through the maze. And every time you get to an intersection, you pick a direction, but before going in it, then and you take your rope with you. But if at some point you reach a dead end, then what do? Well, you can use your rope to get back to the last intersection and make a new choice. But you need to remember that the way that you came from was a dead end. So this is where you use your paint, you put a big X on the ground, and you make sure you don't go down that path again. And if we do this repeatedly, then we are guaranteed to find the exit. It might require a lot of walking because we might have to discover every other dead end first. But with just our paint and a piece of rope, we can solve this maze. If ever you find yourself stuck in a corn maze, see if you can use this too. Now that's the idea of depth-first search. That's great, but this doesn't really tell me yet how I can implement this in Python. So let's take a look at that. DFS. Now, DFS takes a certain vertex, V, to start from. It's our starting position. Now, what do we do? Well, we have a number of choices to make from this vertex, right? All of the different edges leaving this vertex. If they lead to somewhere we haven't been before, in other words, if there's no paint on the floor, right? If it's something we haven't explored yet, then we go there, we mark it as visited, and we do a recursive call from U. Now, at some point, we will have explored U fully, and due to the recursion, we will get back to our node V, and we can now explore the rest of V, or the rest of the neighbors of V. And after we've executed this function, all of the nodes that we can reach from V will have been marked. So we can check, is Haarlem reachable? By simply checking, is Haarlem marked? Now the question is though, what's the runtime of this algorithm? Is it linear in the number of vertices, linear in the number of edges, linear in the number of vertices plus edges, or linear in the number of vertices times edges? Let me see if I can set up a poll for this again. If I remember correctly, this was the syntax. Yes, there we go. Let's see if this works. So what is the runtime of this DFS algorithm? Okay, let's take a look at your votes. 50% for answer D, about 30% for answer B. Okay, well, it's a bit tricky to see, right? It seems to be saying, okay, for every outgoing edge. So, yeah, okay. How many outgoing edges could V have? Well, it could have an outgoing edge to every other vertex in the graph. So that's theta V to go for all the outgoing edges, right? It's not theta E, because V could only have one edge to every other vertex. So it's theta V to go through all of these outgoing edges. And then we need to check if something is visited. Well, that's probably a Boolean, so that's just constant time. Marking it as visited, probably just constant time. Oh, but then we have a recursive call. So maybe for every vertex, we're gonna go through all of its edges. Maybe something like v squared then, right? V times v, but that's not an option. Well, what we do here is we make one more observation. Yes, worst case, we consider every vertex, and for every vertex, all its edges. And yes, worst case, every vertex is connected to every other vertex, so that would make it v squared. But we can be a bit more precise. If for every vertex we consider all of its edges, then that means we consider all of the edges. And that's why answer C is the right answer. We consider every vertex. We do a recursive call to every other vertex. And for every vertex we consider all of its edges, meaning we consider all the edges. So depending on which is bigger, V or E, that one will determine the runtime. If there's way more vertices than there are edges, then that will be the bottleneck. If there's way more edges, then this loop structure will be the bottleneck. So answer C is the right answer. Does that make sense, or are there questions about that? Silence so far. But I should maybe factor in stream delay. I see no questions yet, so I guess it's safe to move on. Could I explain it one more time? Oh, come on. Yeah, just in time. Yeah, sure, I can. So let's start with the recursive call, right? Everything that's not visited, we mark as visited and we do a recursive call on. So worst case, we will do a recursive call on every vertex once, meaning that we will do something for every vertex. So that's a theta v component. Then, for every vertex, we're going to go over all of its edges. Well, if for every vertex we go over all its edges, that means we go over all the edges of the graph. So for every edge in the graph, we also do something. That's a theta e component. So now we have a v component and an e component. And, well, the only question is, should we multiply them or should we add them? Well, for every vertex we do something, but for every edge we also do something, but it's not the case that for every vertex we go over all edges. For every vertex we only go over its own edges, a small subset. So we shouldn't multiply them, we should instead add them together, and then answer C is the right answer. If we wanted to express it only in terms of V, then we should realize that E is bottlenecked or is upper bound by V squared, because worst case every vertex has an edge to every other vertex, meaning E is V squared or OV squared, and then it would be theta V squared. But that's not an option here. So the most precise we can get with these options is V plus E, answer C. I hope that clarified it at least a little bit. It seems to have. Good. Jochem is asking, does the order matter for picking the edges with DFS? No. So this is also great when creating questions about this on the written exam, right? So sometimes I have questions like, here's a graph, give me a DFS ordering of it. Yeah, you can pick the edges in whatever order you like, which makes grading a lot of fun. Okay, I was going to do this, and I was now going to switch over to this one for a second. So here we go. So here is a nice description of a graph. It has 8 vertices and some edges. I'd like you to do number 1 and number 2 of this, please. So please draw the graph for me and give me a sequence of vertices of G using a DFS traversal starting at vertex 1. I'll give you, let's say, 2 minutes to work on this, but again, you can let me know in chat when you're done. Okay, well, some of you are maybe still finishing up drawing this graph. Let's see if I can also start drawing it. So let's see if this works again. It should. So we have 8 vertices. Let me just start here with creating vertex number 1. Vertex number 1 has as its adjacent vertices 2, 3, and 4. It's an undirected graph. Okay, 2, oh. Don't show me an ad, please. 2, 3, and 4. Now, vertex number 2 has as its adjacent vertices 3 and 4. And of course 1, which we already covered. 3 has 1, 2, and 4. There we go. 4 also has vertex 6. Now we get to 5. Okay, 5 has 6, 7, and 8. Back to 6. 6 has 4 and 5, which we already covered. Sorry. There we go. Yes, my apologies. Okay. Let me quickly recap then. So I drew vertex 1 with all its neighbors 2, 3, and 4. Then connected them. 2 and 3 were also connected to 4 and each other. 4 was connected to 6. Then we needed 5, which is connected to 6, 7, and 8. And now I'm working on node 6, which is connected to 4, 5, and 7. 7 is connected to 5, 6, and 8. And 8 is connected to 5 and 7. So I think this should be it. Then let's take a look at the DFS traversal starting at vertex 1. Starting at vertex 1. Okay, so we start over here. 1 is the first one we find. And now it says in the text, assume that in a traversal of G, the adjacent vertices of a given vertex are returned in the same order as they are listed in the table above. So when I do my DFS, starting in node 1, and I ask for the neighbors of node 1, I'm going to get them in the order 2, 3, 4, as indicated on the slide. Which means that the first path I'll go down is this. So 2 is the next one. Now I look for the neighbors of 2. Well, I'm not going to go back to 1 because 1 is already marked as visited. So the next unvisited one is 3. Now for 3, I'm not going to go to 1 because it's marked. 2 is marked, so I'm going to go to 4. From 4, 1, 2, and 3 are already marked, so I go to 6. 6, 4 is already marked, so I go to 5. 5, 6 is already marked, so I go to 7. And from 7, 5 and 6 are already marked, so I go to 8. There we go, a DFS traversal of this graph. Now, of course, what would actually happen now is that from 8, I would go back and now I would double check, okay, did I get everything? Did I get everything? And so on and so forth, right? That's the recursion for you. But here in just one fell sweep, we found the whole thing. No need to backtrack at all. Questions about either the drawing of this graph or the DFS traversal of it? Yeah, so good question, Jochem. What if 1 had another vertex? So consider maybe that 1 would also have a completely separate vertex 9 here. That would be the very last thing we add. Yes. So let me add it in a different color. We can use it for our BFS of this graph later. Let's just call it node 11. If this is also here, then it would go all the way to 8. Now backtrack all the way, and then finally also explore node 11 at the end. Shouldn't we go past all the edges? Well, only if these edges lead to unvisited nodes. And since we've already visited all of them, there's no need to. And you're welcome, Jochem. Good to hear this. Made it clear. Of course, in code.org, we would still be checking for every edge, does it lead to something that is not visited, right? So in code, we would examine all of the edges just to see where do they lead. Do they go to somewhere we've already been? But on a piece of paper, yeah, we sort of implicitly do that. Okay. Let's move us back over to the other slide set. Here we go. Now imagine that you come across this idea of depth first search. I'll hide the blackboard again. And you see this recursive implementation and you think, but that kind of really sucks. Couldn't I do this iteratively? Can I get rid of the recursion? Well, maybe you can. Here's some options for you. Let's see if you can figure out which one would work. And here's a poll for you. Okay, let's see. So, about 1/3 of you for answer B, and a quarter each for A and C, and whatever is left for answer D. Okay, so let's start with answer A. Add nodes to explore to a set and just visit them randomly. It could work to get us a traversal of a graph, but this is not guaranteed to give us a depth first traversal. Right? As soon as we add randomness into the mix here, it's very well possible that we find a different traversal than a DFS one. For example, in our graph from just now, as soon as we add all of the nodes to explore from 1, that would be 2, 3, and 4, and this 11, to this set, then we could take out 4, then we add 6 to this set, we take out 6, and now the next one we could take out could be 11, right? But that's definitely not a DFS traversal. How about a queue then? Well, with a queue, if I add 2, 3, 4, and 11 to the queue, then I'm going to do them in that order, 2, 3, 4, 11, before I consider nodes like 6, 5, whatever else gets added after exploring 4. So again, that wouldn't give me a DFS traversal. A stack would definitely work. And so that leads us to this bit of code. Create an empty stack. Push the first vertex we want to explore, push it onto this stack. And now, so long as there are vertices to explore, meaning so long as our stack is not empty, we take the top one of the stack. And now we can check all of the neighboring vertices. If they are not visited, mark them as visited, add them to the stack, and we're done. So very quickly, what does that look like? Let me show you the code first. If they are not visited, so get them off the stack, check all of its edges. If they're not visited, mark them as visited and push them on the stack. If we try to apply that on our graph of just now, what does that look like? Well, we start does this work? Yeah, we start with node 1. So we have a stack with just 1 on it. Then we take 1 off the stack and we add all of its neighbors. So 2, 3, 4, and let's also add this 11. Now we take the top one of the stack, which is 11. So the order we're building is 1, 11. Now we take 4 of the stack. And in taking 4 of the stack, we can add 6 to the stack. So we now have 6, 3, 2. And in taking 6 off the stack, we need to add all the neighbors of 6. So we need to add 5 and 7 to our stack. So now we take 7 off, and so on and so forth. You see that we get a different order to what we got before. But this order below is still a depth first search traversal. First going to 1, then to 11, then to 4, 6, 7, and then we'll probably go to 8 next. And now we start backtracking. Now we go to 5, backtrack more. Now we go to 3, and then we go to 2. This is still a depth first traversal, just a different one from the one we found before. Does this make sense? This idea of adding nodes to a stack as a way to get rid of our recursion? So if 11 had neighbors, they would appear first on the stack after removing 11 from the stack, asks Jochem. Yes, exactly. thus ensuring we explored these first. No, 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 no. Don't show me a poker ad. Okay. Okay, let's move on. So this was depth first search, one way to traverse a graph. And what can we do with that? Well, we can find out if there's a way to get from one place to another, right? How I can get home to Haarlem. I can test if a graph is a connected graph. Connected graph, connected graph. That means that I can go from any vertex to any other vertex in the graph. I can check whether there is a cycle in a graph, provided that this V, our starting node, is a part of that. But notice that DFS, in the way that we now saw it, only allows us to determine is there a path from A to B, right? Not what is the path from A to B. So what we still need to do is reconstruct a path, and the book tells you how to do this. If you want to puzzle with it yourself first, I recommend you do so. It requires us keeping track of one more thing in addition to this visited. Okay, what else? Well, this is one traversal, depth first search. But how about I take our implementation from just now and I replace only one thing. Instead of using a stack, I use a queue. What happens? Well, surprisingly, we get another nice traversal of a graph. We get what we call a breadth first search, in which, if you want to think of it, it's like pouring water into the graph. Every layer of the graph gets explored one at a time. First, we check all the vertices that are at a distance of 1 from our starting point, then at distance 2, etc., etc., etc. So that is the idea of BFS. Now, let's take our graph from before. Yeah, let me switch this over. Here we go. And now let's give a sequence of vertices visited using a BFS traversal, starting at vertex 1. So I'll give you about 1.5 minutes or so to see if you can conjure that up. A BFS traversal, oh, I forgot the minus sign. A BFS traversal of the graph we saw a DFS traversal of. Okay, the poker ads have stopped playing, so we can take a look at the tablet again. Let me move it back here. resize it a bit. Is already giving us a nice answer. 1, 2, 3, 4, 6, 5, 7, 8. That sounds very similar to our DFS. Let's take a look. Let's take a look. So first we start, of course, still in node 1. And now we want to take a look at all of the vertices at distance 1. So that's 2, 3, and 4, and you can put them in whatever order you like. So 1, 2, 3, 4 will work, but if you want, 1, 3, 2 is also a fine BFS traversal, or 1, 4, 2, 3, anything you want really. All of the vertices at the distance 1 are the ones that should come next. Can I move the blackboard a bit? Sure, I'm not sure where you want me to move it to. Is this better or? Ah, sorry, okay. I'd already moved it down in this corner, but forgot to hit the button to update it for you. Yeah, so this is probably slightly better, right? Okay, so everything at distance 1. Now everything at distance 2. Well, all the nodes at distance 2 that we haven't explored yet is just 6. So whatever happens next needs to be 6. Now all the nodes at distance 3, and that's the last ones. 5, 7, and 8. So again, you can put those in any order. Is this right, what I'm saying? No, it's not. Let me back up a bit. Here we go. Everything at distance 1, 2, 3 is just 5 and 7. So those I can put in whatever order I like. And then everything at distance 4, 1, 2, 3, 4, or 1, 2, 3, 4. That's just the node 8. Is this the mistake you intended to point out, suppressed? Ah, Jochem, do I still need to look at the order of the table? I suppose the question did put a constraint on that, didn't it? Okay. Yeah, it did. Okay. Then I think the one at the top is the right answer, given the order of the table. 2, 3, and 4. 2 adds nothing new. 3 adds nothing new to my queue. 6 does add something new to my queue, namely 5 and 7. And 7 will finally add the 8. Yeah, so then I think it's this one based on if we use exercise edge order. Am I right in saying that, or am I still making a mistake now? Suppress, this wasn't the mistake you wanted to point out, okay. Was it the same one that Jochem pointed out, or is there still something else you think might be going wrong? It's correct, according to Ohm, good. Okay. Let's see, what else did I want to talk about? Let me switch these back again. Yes, exactly, that's what I figured. I had one more exercise planned for implementation, but with 4 minutes on the clock, I know better than to fully attempt it. What I'm going to do instead is quickly talk you through it. And for that, it helps if I put this back up. Give me a second. So I'm going to show you how I would translate. Where is it? There it is. Let me zoom in a bit here, and let me just move this up. I'm going to show you how I would translate this bit of pseudocode into Python. But what I suggest you do is you don't copy everything we're doing now, that I'm doing now, but instead try to understand why I'm doing it, and that you try this exercise for yourself a bit later. Right, but then at least you've seen it done once, and then let's say this afternoon you try and see if you can implement it yourself. Now, someone already asked, is there a way to have a queue in Python? And there is. Remember that we have the DQ for that. So let's translate this code as closely as we can. First, we need an empty queue. Okay. There we go. Now I need to enqueue our first node. Then what else? We need to mark this node as visited. Okay. Visited is some dictionary or is some set. And visited is going to contain M, our starting node. Now, while S is not empty, take, and of course enqueue is not the name Python uses, right? It is indeed append. Thank you, Jochem. And to remove was pop left, if I recall correctly. So that's to dequeue. And then for every edge that our node has, okay, let's take a look at the library code. A node has a set of neighbors. Okay, great. So for neighbor in neighbors, is that what we call it? Yes. If if neighbor is not in without the word is, not in visited, then what does my pseudocode say? Mark it as visited. Okay, so visited.add neighbor, and we should now make sure we go and explore it. So we should append it to our S. Now there's just one thing. Right now we have everything in visited, but we actually wanted to return a list of vertices. So we should build some sort of result, and everything we take off, we will add to our result. It's a list of integers, so it's a list of their IDs. So this should be it. Let's see. How many mistakes did I make? Yeah, okay, it's not called pop left. Let me take a quick peek at what it is called then. It is called pop left, but without the underscore. So there we go. Still a mistake. What am I doing wrong? I'm using append. I'm adding it to the visited and to the queue to explore. Okay. I think I see. Yeah, I'm indeed doing the neighbors in reverse order. I should use get neighbors. I hope that our text says that we should. Yeah, the function get neighbors in the library class already returns the neighbors in an ascending order of their values. Okay, so let me get back to my code. Instead of going through the neighbors, I should ask G to get me the neighbors of current and go through them in that order. This is just to make our spec test work. There we go. There we go. So that was very quick, 4 minutes, me implementing BFS. Again, I strongly recommend that you take a look at this exercise yourself. But now that you've at least seen me do it once, perhaps it will come a little bit quicker and easier for you to attempt this exercise. Okay, with that, we have reached the end of this tutorial. Yesterday during the lab, I noticed that some people got Talkie working. That's good to see, right? You can still interact with our TAs and ask them questions if you have them. For Talkie, please know that there's no need to turn on your webcam or anything like that. It's just for voice chat. And even if you don't want that, or if you don't have a microphone, you could use Talkie just for text-based chat as well. But at least it allows you to still interact with a TA and ask questions if you have them. I have no idea why you were timed out by Nightbot Cisco X, but apparently you tried to post a link. Okay. Okay, I think that should do it for today. I'll stick around in chat for 5 to 10 more minutes to answer any questions if you have them. And otherwise, I'll see you back on Monday. And on Monday, we will be talking about graphs a little bit more, focusing not on is there a path from A to B, but what is the shortest path from A to B. So we will indeed be talking about Dijkstra's algorithm, something that many of you may or may not already have heard of. So with that, I'll see you on Monday.